All right, so chapter 18, it's a nice, easy, short chapter that talks about equilibrium associated with solubility. All right, now you remember solubility, right?
I have the solubility rules.
That's right, good. So we have rules associated with solubility of ionic compounds, right? And those rules tell us whether a compound is soluble or insoluble, right?
Yeah, that's right.
And I could say something like iron carbonate, soluble or insoluble?
Let me check the rules. Carbonates are insoluble. So insoluble.
Iron carbonate, insoluble. So you went to the rules and you found out that carbonates are generally insoluble, right? And, you know, that's good. That's good, right? We just said something is soluble or insoluble. However, it's not that simple in reality, right? Everything is soluble to at least a little bit. And that's because, for example, here's silver chloride. Silver chloride, look at your rules. Is that soluble or insoluble?
Chlorides are generally soluble, but it says that, I got a hair in my eyes. Can you help me with that?
Yeah, sure. Get that out of your eyes. There you go.
Thank you. Chlorides are generally insoluble, but, sorry. Chlorides are generally soluble, but silver is an exception. So silver chloride is not soluble.
That's right. But when we put silver chloride into solution, a small amount of silver ion results and a small amount of chloride ion results. When they find each other, they go back. But this is an equilibrium. And we didn't have the ability to speak about equilibriums when we were talking about solubility a long time ago, so we didn't really bring this up. But all compounds can, all compounds, insoluble ones, can dissolve to a certain amount. And so we have a K value, and now let's write this expression down here. Silver chloride, AgCl, dissociating into silver ions and chloride ions, right? What's the mass action expression or the equilibrium expression for this value?
So you have silver ion times chloride ion concentration.
Very good.
Over silver chloride.
All right, but silver chloride is solid.
Oh, yeah, solids aren't included, so just over 1.
That's right. So the K for this reaction equals, and we really don't need to have that part in there, the silver ion concentration times the chloride ion concentration. So the KSP, whatever the value is, will be equal to the product of these values. And if you just put silver chloride into solution, then any amount of this material that appears, again, looking at the ice table, AgCl going to Ag ion and Cl minus. If we think about an ice table, initial concentration, it doesn't really matter whatever you put in because it's not soluble. But I'm going to start off with nothing here. And so the change is going to have to be plus x, and at equilibrium, the concentration of silver ion will be equal to the concentration of chloride ion because they went in at, for every 1 unit that dissociates, you're going to get 1 of each of these. Okay? So, the actual concentration of, in this case, silver or chloride ion will just be, or x, right? X will just be the square root of 1.8 times 10 to the minus 10. So we can, for example, look at our silver carbonate, write the mass action expression. It's going to be the concentration of carbonate over the concentration of silver squared, right? Can you see that?
Oh, yeah, I see that.
Concentration of silver squared, concentration of carbonate, that's going to equal our KSP. How about this one?
Concentration of ammonium ion squared times the concentration of sulfate.
Very good. So we can write the mass action expressions for these just as we did before. Again, we're just recognizing and emphasizing that we don't include the solids, right?
Yeah.
Now, the molar solubility, how much actually dissolves, right? Because when I take silver carbonate, for example, put it into solution in 2 silver ions and 1 carbonate ion for every mole of this material that will dissolve, right? my KSP, my K for this reaction, whatever the value is, the X value here, what I solve for, will be the molar concentration that actually ends up being in solution. So the molar solubility is the amount in moles that actually is soluble. So I can solve that. KSP, 1.8 times 10 to the minus 10 for silver chloride. X squared, which is the concentration of my silver ion times the concentration of my chloride ion, set it equal to 1.8 times 10 to the minus 10. Take the square root of x, or sorry, square root of x squared, square root of 1.8 times 10 minus 10, 1.3 times 10 minus 5. And the units are molar. That becomes the molar concentration of silver ion, the molar concentration of chloride ion, and the molar amount of silver chloride that dissolved. Okay, does that make sense?
Yeah, that's pretty straightforward. It's the same as before, right?
It is, but we're talking about an equilibrium of a solid dissolving. And so the K, it gets this little SP to help us realize, oh, we're talking about the solubility product, they call it, because it's kind of the product of the two units, or the whatever is, it doesn't necessarily need to be two, like in the silver carbonate example, right? There ends up being 3 entities, 2 silver ions and a carbonate. But the KSP stands for solubility product. If you forget what the SP stands for, it doesn't matter. You don't need to remember. You just recognize that it's a K, and you need to know the reaction for which K you're talking about. Uppercase K, right? So what's the molar solubility for the calcium phosphate at 25 degrees Celsius? Here's our KSP. So 2 times 10 to the minus 29 is equal to what? What do I have to set that equal to?
Set it equal to the concentration of calcium ion cubed.
Very good. Concentration of calcium ion cubed.
Times the concentration of phosphate ion squared.
Phosphate ion squared, right? And that's going to equal 2 times 10 to the minus 29. All right, so now I can throw in an X for each of these, right? However, I have to recognize that in my ice table, there we go, for every 1 unit here that dissociates, I get 3 calcium ions. For every 1 of these that dissociates, I get 2 phosphate ions. So the concentration of calcium ion at equilibrium is going to be the 3x. The concentration of phosphate ion at equilibrium is going to be 2x. So I need to throw in 3x in here and 2x in here, and then set that equal to 2 times 10 to the minus 29. All right? So what's 3x cubed?
3x times 3x times 3x?
Yeah.
Is that 9x cubed?
Well, almost. 3 times 3 is 9, but then 9 times 3.
Oh, yeah, 27.
All right, so 27, 27x cubed. Now times 4x cubed, 4x squared, right?
Yeah.
4x squared. What's 27 times 4?
I'm not sure.
27 times 4, 108. So this equals 108. And what do I do with my x's?
You add those exponents, right?
X to the 5th. That's right. 108x to the 5th. And that equals 2 times 10 to the minus 29. Okay? So I take 2 times 10 to the minus 29. Divide by 108. Get the x's all by itself. And then I take the 5th root, right? Because this means x to the 5th equals 1.85 times 10 to the minus 31. Well, how do I take the 5th root? There's a way to do it in here, and you can search for it, learn on YouTube. But what I do, let me pull this out a little bit, is I just raise it to the 1 over 5. Because let's see, the square root of x is equal to x to the 1/2 power. The 4th root of x is equal to x to the 1/4 power. Okay? So you can just raise it to the 1/5 power. All right, so I raise it to the 1/5 power equal, and I get 7.1 times 10 to the minus 7. X equals 7.1 times 10 to the minus 7. And that is the molar solubility. 7.1 times 10 to the minus 7. That's how many moles of this material dissolve. That's not going to be the concentration of calcium ion, and that's not going to be the concentration of phosphate ion. The concentration of phosphate ion is going to be 2 of these X's, right? It says right there. The concentration of calcium ion is going to be 3 of these X's. But that is going to be the molar solubility, the moles of this material that actually dissolves. Okay, great.